The part for linear response relations turned out to be longer than I first thought. I think I was lecturing for more than 40 minutes. But this part, which is basically a continuation, should be much shorter. And now we can discuss reciprocal relations, which I believe are the most important results in non-equilibrium statistical mechanics. So to motivate reciprocal relations, I like to discuss something called thermoelectric effects. And examples are the Seebeck effect, the Peltier effect, and the Thomson effect. But don't ask me what they are. I'm always confused which is which. But anyway, these effects say briefly that heat current and particle current, in many cases electrical current, may couple with each other. And this may sound a bit surprising because heat current is just heat current and particle current is particle current. They are very different. But let me discuss a very, very simple example of Brownian particles, which I think will convince you that this kind of coupling can take place. Okay, so again, consider a system of Brownian particles, but in this kind of potential. So it's constant here, and here's a step, and it goes down, and it's constant here, and another step, and it goes up, and we have periodic boundary condition. And the trick is that around here, the system is coupled to heat bath number 1, and around here, it's coupled to heat bath number 2, okay? And here is the basic energy exchange process between the heat bath and the system. So suppose that particle is here, and it goes down this step. And then it gets extra energy V, but this Brownian particles, it doesn't accelerate, and it again slows down. So it should release this energy to the heat bath. So in this process, energy V goes from the system to the bath. And this is opposite. If it wants to go up, then it should get energy V from the heat bath. And this is basically the same. It gets energy here, and it releases energy. Now, okay, suppose that beta 1 is larger than beta 2. So this means that this one is hotter than this one, hotter than this one. So then there should be a heat flow from bath 2 to bath 1. Now I assume that this process gives the dominant energy exchange between heat bath and the system. With this assumption, in order to have heat flow from bath 2 to bath 1, you have to have the situation that okay, so heat wants to come from here and go here. So for heat to come in from bath 2 to the system, you see that this process should happen more often than this process, right? And similarly, the heat should go from the system to bath 1. So this means that this process should happen more often than this process, okay? So these are the number of the processes. But what does this mean? Well, you have more this than this. This means that particles go down, go in this direction, and you have more of this than this. This means that particles go more often like this. So you see that since we have periodic boundary condition, you see that we get particle flow from the left to the right. So in this case, we didn't apply any force, but this temperature difference induced particle current. And similarly, now here, I assume that that heat baths have exactly the same temperature, but we apply this non-conservative force to particles. Then, of course, this particle non-conservative force induces particle current. But since if particle current is there, then of course you have more of this process than this, and here more of this process than this. But this means, again, that then, again, assuming that these are the dominant energy exchange, then this means that heat flows from bath 2 to bath 1. So there is a coupling. Here, let me add this remark, see problem 4.1. So the discussion here was a bit vague and abstract, but if you look at this problem 4.1, you will see a concrete example of 3-state in which this idea discussed in page 15 is realized concretely. So here, I just defined these transition rates corresponding to this situation with different temperature and the same temperature and all the same temperature and non-conservative force and so on. So, and you can compute everything explicitly. So I encourage you to look at this problem to understand this discussion better. So yes, so this is already what I said. So to quantify this, let me denote JH, the heat current, and JP, the particle current. And then, first of all, I assume that F equals 0, no force, and there is a small temperature difference. And then this is what we already discussed, okay? Small temperature difference induces heat current, and this is a linear response coefficient that we were discussing. But now here is something new, okay? We have this temperature difference, but it induces a particle current. So here is a new linear coefficient, linear response coefficient. Similarly, we have no temperature difference, but a non-zero, non-conservative force. Then in this case, this is something we already knew. So this beta F, we denoted this as epsilon, induces particle current. Okay, but again, something new. This epsilon, this force induces heat current like this, and here is a new linear response coefficients. Okay, and Onsarga's reciprocal relation says that these two linear response coefficients are exactly identical. Okay, so this kind of identity was first pointed out by Thomson, Lord Kelvin, back in 1854. Well, Thomson is a gifted person. He's clever, and he found many things for the first time. But in satisfactory derivation was given by Onsarga back in 1931. Okay, but anyway, isn't this surprising? I mean, it's not very surprising that temperature differences induces particle current and force induces heat current. This connection may not be very surprising, but it's very surprising, at least to me, that these constants are exactly the same. So I would say this is surprising or even miraculous symmetry. And when you have such a symmetry, you usually expect that there is some structure, some nice structure behind this symmetry. So here is a good analogy. So in equilibrium thermodynamics, we know something called Maxwell relation. That is very, very surprising. Okay, so it says that the particle number dependence of the pressure is exactly equal to the minus of the volume dependence of the chemical potential. Well, if you are simply given this identity, this is just a miracle, just surprising. But behind this, we have equilibrium thermodynamics. And actually, this comes from this very simple mathematical identity. Okay, so you want to consider twice derivative of the Helmholtz free energy, and these two are the same, and this simply gives you this. So in this case, this is a miraculous symmetry, and in this case, behind the symmetry was equilibrium thermodynamics. Okay, so but in this case, we don't have equilibrium thermodynamics behind this. This is purely non-equilibrium phenomenon. And Onsarga pointed out that behind this symmetry is time reversal symmetry. But anyway, we want to derive this in our setting. Okay, so this is our general setting. So we consider a system with two different non-equilibrium parameters that we call epsilon1 and epsilon2, and then we consider the corresponding non-equilibrium current J1 and J2. Okay, and then these are two examples. The first example is the thermoelectric effect that we discussed already. So we have two heat paths which may have different temperatures, and this temperature difference is denoted as epsilon1. And then the corresponding current is heat current from the system to this bath number 1. Okay, and the other non-equilibrium parameter is that for non-conservative force. So we have to impose periodic boundary condition. I don't know how to do that, but anyway, suppose that it was possible. And then this second non-equilibrium parameter is this. Okay, and the corresponding current is particle current. But we can have much more realistic situation with 3 heat paths. So this is one heat bath, which is reference. And here is one heat bath with temperature beta plus epsilon 1, and the other heat bath with beta plus epsilon 2. And in this case, current J1 is heat current from the system to this one, and J2 is a heat current from the system to this heat bath. So in this case, what we consider is like this. So you first suppose that this epsilon 2 is 0. So the temperatures here are the same. So you usually don't expect any heat current here. But here we have non-zero epsilon 1. So we do have big heat current from here to here. And in some case, this heat current induces heat current from this bath to this bath. They have exactly the same temperature, but still there can be heat current. And similarly, if this is 0, but this is non-zero, then we have this heat current. But then this may induce this heat current. And in these inductions, there is a beautiful symmetry. Okay, that is reciprocal relations. And here is just a notation. By this, we denote the expectation value in the corresponding non-equilibrium steady state. Page 6, well, this is just for trivial, but let's go back to page 6 of this part 4. So here, I just simply discuss stationary distribution under non-equilibrium condition and the corresponding transition rates. So this is the standard expectation value of a jump quantity, but I abbreviated this like this. But now in this case, we have non-equilibrium steady state with 2 parameters. So this will have 2 parameters like this. Okay, now we want to derive reciprocal relations, the reciprocal relation, but actually it's done in this single slide. So the most basic part is already done in page 11 of this part. So in page 11, we discussed this relation. So soon after this, we set J to be J, and we got this fluctuation response relation. But this was original, more general relation. So here in this relation, G was just an arbitrarily asymmetric jump quantity, and J is something related connected to this non-equilibrium environment. So we had this. So anyway, we copied these relations here. So these were general relation. G is an arbitrary asymmetric jump quantity, and J is something directly connected to non-equilibrium nature of epsilon. So we apply this to our situation. We first assume that the first parameter epsilon 1 is 0, and we look at the expectation value of J1. And then by definition, this linear response coefficient is written L12. And from this relation, we see that this L12 has this representation. So here, J1 plays the role of G, so we have here. And since this is epsilon 2, J2 plays the role of J. So we have this time-dependent correlation function, integration, and limit. But anyway, we have this. And we consider the next thing is that we assume that epsilon 2 is 0. Epsilon 1 is non-zero, and we look at the expectation value of J2. Okay, and then the corresponding linear response coefficient is represented like this. Now, in this case, J2 plays the role of G, and J1 plays the role of J. Okay, now we have this expression, time-dependent expression, integration, and limit. Okay, and as I said before, we are not able to compute these correlation functions or integrals in general. And here, of course, we are doing very general discussion, so we can never compute them explicitly. But look, this is not quantum mechanics, so you can exchange these engines. And you can change variable S and T. You see that they are exactly the same. These two integrals are exactly the same, so of course the limits are exactly the same. So we don't have to compute anything, but we can conclude rigorously that these two coefficients are exactly the same. So this is a proof within our approach in Markov jump processes of the reciprocal relation, the reciprocal symmetry. So I can say, sorry for the messy character, so I can conclude that a remarkable symmetry can be explained in terms of linear response relations. So behind the linear response relation is this detail fluctuation theorem, and behind detail fluctuation theorem is a kind of time reversal symmetry. Okay, so anyway, so we were able to derive this kind of beautiful symmetry. Okay, so these were all for linear response relations and the corresponding closely related reciprocal relations.